All right, this week we're going to talk about solid state chemistry, which is a little bit different than some other areas of chemistry that you've experienced. And we'll focus on some structural information and some types of calculations that we can make. And a lot of this requires you to look at several examples in the book or online to get really comfortable with the ideas. So I'm going to share my slides with you. And these are some of them have nice pictures to look at, and some of them are more like calculations. So here we go. Oops. This week there will be a total of 4 recorded presentations. So solid state chemistry. So let's take a look at the, let me get my pointer here. Let's just take a look at a couple of pretty structures here. So along the bottom are carbonite, wellerite, cliniclase, and fluorite, which are just some interesting crystalline structures. A lot of what we're going to talk about is crystal structures and how we describe those and talk about them, and how we can make some calculations relating to them. So let's get started. So we can classify most crystals into one of 7 families, right? We have these 7 crystal systems is what they're called. And so they're formalized forms are shown here, ranging from cubic, which is about the simplest, where we have all the sides being equal, hexagonal, which is probably our most complicated structure in this group. So these are the 7 crystal systems again. So the information about those is summarized in a table. There's a table similar to this in your book. You can also get a table, probably this exact table actually online. And it just talks about the different systems. They're listed in a different order than the previous slide. It tells you how those parameters are related to each other. So the height, the depth, the width, are they equal, are they not, and what are the angles between them? We're going to be talking about something called a unit cell, and sort of basic definition of a unit cell is something that describes the 3-dimensional shape that's the building block for the crystal structure that we're talking about. This particular table includes some symmetry information because, of course, we can treat crystals with the symmetry information that we looked at before. So let's take a look at some of the simple structures and some unit cells and talk about how those fit together. So on the left here is a simple cubic structure. Ball and stick model is at the top. A space filling model is shown in the middle. And in crystals, we often then sort of cleave off the sides so that we can see what portion of the atom is inside the cell versus what portion of the atom is outside the cell. And then a larger expanded structure is shown at the bottom here so that you can see how the unit cells fit together and how the atoms fit in a larger crystal lattice. So in a simple cubic cell, atom at the point of each corner of a cube, right? So there's a big hole in the middle, and the holes will become important in a little bit. So just try to keep in mind where the atoms are and where the holes are in these structures. So the next kind of structure that we want to talk about is body-centered cubic, and this one will be pretty important. It's very similar to the simple cubic, except that in addition to the atoms on each corner, we have an atom then in the middle. And so you can see in the space filling model sort of how they fit together, and they're all touching inside. It's important to note that they're touching each other. And then you can see how the unit cell fits together down here. And then the third one we want to talk about right now is face-centered cubic. It's a little hard to see in this top one, I think, but we have the same atoms on each of the corners. And then additionally, we have an atom that is in the center of each face of the cube. You can see how that fits together down here. So let's talk about the idea of a unit cell for a little bit. So this is the unit cell here in the central portion, and the unit cell describes how the atoms fit together, essentially. And if you repeat the unit cell by stacking them and setting them next to each other, then you can recreate the simplest information to communicate that fully communicates the structure of the larger crystalline solid. So in the cutaways in the middle here, you can see that on the corners, for example, although there's an atom at each corner, only 1/8 of that atom is actually inside the cubic cell. So the total number of atoms inside of this simple cubic unit cell is just one. There's one atom inside there. In the body-centered structure, we still have 1/8 of each corner atom inside, but then we have one whole atom inside in the middle. And so there are 2 atoms inside of the body-centered cubic structure. The face-centered cubic structure is a little bit more complex. We have 1/8 of each cell as one atom. And then the ones on the face, half of each atom is inside. And there are 6 on the faces. So that means there are 3 atoms inside from these sort of facial atoms here, plus 1 more for the corners. It's just a total of 4 atoms inside the unit cell. So there are other ways to think about how the atoms are nestled together and how their structures are put together. And so we can talk about a concept called close packing. And in a close packed structures, the atoms are as close to each other as they can get, and they fill the holes as best they can. Remember, they're still spheres, and so when you stack spheres together, you're going to have holes. But on the top structure here, you have 2 different colors of atoms. Now, that if you imagine that you're filling a box with ping pong balls, perfect first layer of ping pong balls, which of course represent atoms in our case here, and then you start to add another layer of atoms on top of that, or another layer of ping pong balls. Then the next layer of ping pong balls, they'll nestle down in the holes between the atoms or between the ping pong balls in the first layer. And so for clarity, they're shown here in different colors. Now, once you've made 2 layers, there are 2 different things that can happen. If you add a 3rd layer, one thing that can happen is that 3rd layer of atoms will rest directly above atoms in the first layer. And so if we give them names, so this first layer is type A, and then the second layer we call B, it nestles into the holes. If the 3rd layer is directly above atoms from the first layer, we can call that A again. It's this sort of diagram, and we'll see in just a minute that results in a particular kind of 3-dimensional structure. On the other hand, if the 3rd layer of atoms nestle into a little bit different place on the 2nd layer, then they will not be directly above the atoms in the first layer, and we'll have a 3rd sort of geometric position. So we have a different layer from the first 2. So there are 2 possibilities. 2 things to keep in mind. One is, where are the atoms? And the other is, where are the holes? So let's look at the 2 close packed structures that arise from these 2 different kinds of layering. The first one that we want to look at, and the one that was on the top on the slide before, is called hexagonal close packing. And the unit cell for this, we have a set of atoms on the top, right? Those are these in the space filling model. A set of atoms that nestle inside below that, and then another set on the bottom. It has a hexagonal 3-dimensional structure. The other that can form, and the color coding is the same here, and there's a diagram at the top and then a diagram at the bottom, is a cubic close packed structure. So these atoms are just as close to each other as they can get. This is a face-centered cubic structure, right? And the layers are kind of tipped over on their side now. So layer A was blue, layer B was this kind of pink color, and layer C was this green color. And so you can see that the cube here is cut out of those diagonal layers. So let's talk a little bit about the types of holes that can form between the atoms here. So if we have a set of 3 atoms and we stack 3 atoms on top of those so that they're kind of rotated a little bit, in the center there, that's called an octahedral hole. And that's because if you connect all the faces, it would have 8 faces and be an octahedron in that space. So we have this little pocket in between here. And what's going to be important for solid materials is that you can fit things into the holes. Other atoms, other ions, complete molecules sometimes will fit in those holes. And so the size and the location of these holes becomes important then. So this top one is the octahedral hole. The bottom one, so we have a layer of 3 atoms and then 1 additional atom goes on top, or as it's shown here on the bottom. Then we have a hole that results there. It's called a tetrahedral hole because there would be 4 faces if we made it into a 3-dimensional structure. We can calculate the size of the holes, and the equations are shown here on this slide, right? And the size of the hole is based on a couple of things, but it primarily depends on the radius of the atoms that are composing the structure. So how big are the spheres that are building up to form these crystalline structures? And that is really what determines how large or how small the hole is where something else could fit. So let's look at a couple of examples now of what kinds of calculations that we can do. And one thing we can calculate is how much of the unit cell is occupied by atoms, or we can calculate how much of that space is actually empty space between the atoms. So in order to calculate the percentage that is occupied or the percentage that's unoccupied, we need to know a couple of things. One, we need to know the volume of the unit cell. So how big is this whole cell? And then we need to know the volume of the atoms that are inside that unit cell. Calculate the fraction or the percentage. So let's take a look at our example here. In this case, we have a face-centered cubic structure. And so that means that it's a cube, so all sides are equal, A, B, and C. Well, I guess we call them A on all of these since they're all the same, right? They're all the same length because it's a cube, and that means that if we have, we want to determine this distance here. Okay, so the radius of each of our atoms we'll call R, and across the face, where we have a face-centered cubic structure, we have this blue atom here. We have all the way across this red atom, so that's twice the radius of the atom. And then we have the radius of this green atom over here. So for our purposes, they're essentially the same. The same type of atom. So we can calculate then the length of the side if we didn't already know the length of the side. And so the math is shown here, but the length of side A is the square root of 8 times the radius of the atoms. So all we need to know at that point is the radius of the atom, which is probably something we can look up and plug that in. So we can calculate then the volume of the unit cell, because the volume is going to be the length of the side cubed. Gives us this value here, right? So we just take the 8 times the radius, cube it. You can also write it in this other way. I've shown both here because you see both in various textbooks and various resources. Okay, so once we know the that information, we need to still find how much of the unit cell is occupied, right? So each of our atoms is treated as a sphere in this case. And so because this is a face-centered cubic structure, that means there are 4 atoms inside, and the radius of any sphere is 4/3 times pi times the radius cubed. And so we can simplify that a little bit. It'd be 16/3 times pi times the radius cubed. So then we would just still need to plug in the radius for our particular atoms, right? So if we just want to get a rough idea of what is occupied or what is unoccupied, then it actually works out pretty nicely that the volume terms or the radius cubed terms will cancel out. And so for a face-centered cubic structure, if we plug in the occupied volume on the top here over the unoccupied, over the total unit cell volume, then the R cubed terms cancel out, and the rest is numerical. So we can calculate that 0.74 is the fraction, or 74% is occupied by atoms. The unoccupied fraction then is just the difference between that number and 1, which means that about 26% is unoccupied. A lot of the time you can work these out even if you don't know the radius, because the term that you don't know will end up canceling out. All right, so let's look at a little bit different example and try to calculate the largest sphere, or the maximum radius for a sphere that would fit into an octahedral hole. And so the diagram is shown over here for an octahedral type hole. And this little pink part is the representative of the atom that would fit inside there. And the distance between the centers here is twice the radius of this atom. And this side is the radius of this atom plus the height of this hole, RH. How can we work that out? We need to find this value. So from our sort of basic geometry classes, we know that a squared plus b squared still equals c squared, and we can plug in our values here. So we have 2r squared, and then we have 2 times r plus rh that replace our a and b terms, and then that whole term is squared. And if we go ahead and crunch through all the math for that, we find that the maximum radius, or the size of that hole, is 0.414 times whatever the radius of these blue atoms is, or these purple atoms. So we can always calculate, or at least estimate, what size atom would fit inside this hole. So people have done a lot of work and investigated a lot of different metals, and you can find these tables. This particular one, I think, is from Shriver and Atkins, Inorganic Chemistry, but there are a variety of them online. And they show you in a sort of schematic way what type of formed by various metallic elements at room temperature. And we'll talk about this a little bit more. If you change the temperature conditions, then these don't hold true because many metals can have different structures at different temperatures. But you can see that the alkaline earths, for example, for the most part, are hexagonal close packed at room temperature. The alkali metals are body-centered cubic, for example. And distributed through here, we also find some cubic close-packed structures. So you can always look these up, but it's interesting to look at some of the trends for which types of elements form which types of structures. Another kind of calculation that we can do is we can calculate the density based on the structure. So let's look at an example. Let's calculate the density of gold, which forms a cubic close-packed array of atoms and has a cubic lattice parameter of 409 picometers. So what exactly does that mean? Well, that's the length of the side of the atom, of the unit cell. Okay. So for our purposes, we can treat a cubic close-packed structure as a face-centered cubic structure. They're essentially the same thing, it's just different names. And in order to find the density, we need to have both the mass of the atoms that are in the unit cell, and we need the volume of the unit cell. That look like? So density is mass over volume. In a face-centered cubic cell, we have 4 atoms, and so we have 4 times the molar mass. And then we need to divide by Avogadro's number to get us back from moles of atoms to single individual atoms. And then the volume is going to be equal to that length, that cubic lattice parameter cubed. And so we find that a sample of gold, solid at room temperature, should be about 19.1 grams per centimeter cubed or grams per milliliter, depending on how you like to think about it. So those are some of the calculations. Let's take a few minutes and look at some of the structures a little bit more closely. One of the things that's interesting about metals in particular is that some of them have different structures at lower temperatures. So cobalt is an example, and above 500 degrees is cubic close packed. But if you cool it down to room temperature, it transitions into a structure that is essentially randomly packed. The atoms are still packed close together, but not in such a crystalline structure. So this kind of property where elements exhibit different structures at essentially different temperatures or different physical parameters, then we find that those are exhibit polytypism or are polytypic. So polytypic elements and compounds exhibit structural modifications based on the stacking of the atoms in the structure, and typically differ only by the sequence. Let's look at a couple of the non-close packed structures. What we've been talking about up until this point are pretty much close packed structures. Body-centered cubic we looked at a little bit before. Those are common for metals, especially tungsten and the others that are shown here. And it's so common for tungsten that it's actually called the tungsten type arrangement sometime. Remember that body-centered cubic means there's an atom at each point plus an atom in the center. Primitive cubic structures only have atoms at the corners of the cube. They're actually very easy to deform because they don't have any atom holding them up in the center. So they're relatively uncommon. Polonium is one example where we do see that. And then solid mercury has a related structure. Remember, mercury is liquid at room temperature, but modified at cold enough temperatures. And it has sort of a distorted cubic structure where it's basically a cube, nothing in the middle, nothing on the faces, but kind of squashed over to one side. Sometimes we have metals that have more complex structures, but they're really distortions of simpler structures. So zinc and cadmium, for example, as pointed out here, they are essentially hexagonal close packed, but the layers are separated a little bit. And what this suggests is that the bonding between atoms in the same layer is stronger than the bonding between atoms in different layers. So polymorphism is the ability to adopt totally different crystal forms under temperature and pressure conditions. So polytypism, like we looked before, is where the stacking sequence changes, but polymorphism is completely different crystal forms. So in some cases, and especially this is true for metals, they have a body-centered cubic structure at high temperatures, but then if you cool them down, they settle into a close-packed structure. And that probably is due to increased energy at higher temperatures, which increases amplitude of atomic vibrations and separates those atoms a little bit from each other. All right, the last thing we're going to talk about in this set is alloys and their various types. So on this slide, I just want to introduce the 3 types of alloys, and then we're going to look at some specific examples with some diagrams on the next page. So an alloy is a blend of metallic elements, and we usually prepare these by heating up the different kinds of elements together and then cooling them down to produce a solid. So the 3 types are substitutional. In a substitutional solid solution or alloy, we have replacement of one type of metal atom by another type of metal atom. Interstitial is where we have atoms occupying holes. And intermetallic is where we have combination of 2 different metals, but the alloy forms a completely different type of structure than either of the metals that we put in. So let's look at some diagrams. For substitutional solids, so these are the first kind, we have replacement of atoms in the lattice, right? So that's this one at the top here. The green atoms represent sort of the original metal, right? And then we have replacement of those by the other atoms. So the red atoms have replaced some of the green atoms in the lattice. This is pretty common for elements, for alloys, excuse me, that are composed of elements that are similar in size. It's also very common if both of the metals being combined typically have the same crystal structure. And it's common if we have metals that have similar electropositive characters. Some examples are shown here at the bottom. Copper and nickel are common mixtures in alloys. And we have some brasses made of copper and zinc that also fit in this category. So interstitial solids is the next type, and the 2 at the bottom, so B and C shown down here, are both interstitial type alloys. And in interstitial, the secondary kind of atom fills the holes between atoms. And so if you have a sort of small number of your second type of atom, then you get a structure like this. You can also have mixtures where they're essentially alternating, or they've formed lattice kind of almost inside of each other. All right, so that is it for this particular presentation. There's more information about, oh, let me stop sharing here. There is more information about crystalline solids and solid state materials, including information about semiconductor materials in some of the upcoming ones, and there are a total of 4 presentations.